Hey, good evening, everyone. So, last Monday we did do a little bit on what we call the classical machine learning algorithms. So far we have been doing kind of first principles, looking at classical regression problems, the linear regression, the logistic regression, right? Using first principles, basically, doing it all from scratch, just so that we have a very good understanding of the, of all the basis of the first principles behind it. Now, we are going to look at using some additional, advanced methods. Yeah, I remember I ended Monday class by showing you how we can do the classification and regression that we have been doing, you know, by using sklearn. And so in using sklearn, we were able to see how much easier it is. Because with sklearn, you basically just call a function called linear regression or a class called linear regression. You create an instance of it, and then you pass the x and the y values, and it does the regression. And I remember a lot of people on the chat were like exclaiming, wow. And we have been suffering since. Well, it is good to know these principles, right? Because it really grounds your knowledge. Now, when we begin to talk about why should you train for so and so many epochs, and why should your learning rate be this value or that value, it makes more sense to you. You can tell the relationship between learning rates, gradient, right, and um, the overfitting, the explosion, gradient explosion, or gradient, vanishing, because you understand that. And then you can also understand how hyperparameters like the learning rate and the number of epochs that you use in training, right, are influenced by the gradient, and how the gradient is influenced by the magnitude, the order of magnitude of the data, that you are crunching. So basically, these are all very important. You wouldn't understand it if you just use sklearn to do something. sklearn will probably just normalize it for you or standardize it for you, and you wouldn't understand. You also wouldn't understand why you are normalizing or standardizing. In fact, one of the challenges I want to ask everyone here to do is take the second logistic regression problem or linear regression with multiple variables, the problem I gave to you, and try three different approaches. In the first approach, do not do any normalization. Do some experiments, right? And then let me know how many epochs it was and what learning rate you had to use and how many epochs it took you to converge and what was the loss. Then after that, that's the first experiment. The second experiment, the same problem, but you normalize only the y, the x values, right? Don't normalize the y values. Normalize only the x values and then run again. And let me know your loss. Let me know how many epochs it takes to converge, right? And you probably still get the same answer, even though your coefficients will be different, your parameters will be different, right? But when you do the prediction, it will be the same. And later on next week, we are going to look at metrics, how you measure the performance of your models. When we talk about the RMSE, the recall precision and all of that, right? So that's how you can use when you're doing those experiments to compare that the models are performing well, right? So that will be the second experiment. The third experiment would be do the same thing, but this are like around normalize both the X values and the Y values, right? And then see the difference. I've actually done that experiment. Maybe I can share my notebook, but I would like you to do it yourself. So you would see that when you normalize, you actually converge faster with less epochs and with a higher learning rate. But when you don't normalize, you need to lower the learning rate to avoid your gradients from exploding, right? Well, your gradients will definitely blow up, but the learning rate will reduce. So it will still learn, right? But because you are using a much lower learning rate, you have to run more epochs, sometimes 500,000 to 1 million. with a very low learning rate of 0.001 or so. That is if you did not normalize anything. But if you normalize the X values or the Y values, you can use a learning rate of 0.01, and 1,000 epochs is enough to converge. Interestingly, one of the things I found is that normalizing the Y value did not make much of a difference. It still kind of converged in 1,000 or so epochs with 0.01 learning rate. So doing these things gives you a very good intuition about machine learning. This is what you need to have. You need to have in-depth, deep understanding, intuitive understanding, rather than just a shallow thing. Then these tools here are just to speed up your productivity, right? So you don't have to write them from scratch, but you should do them with a good understanding of how they work. So today we are going to look at decision trees, random forests, and then we're also going to look at how gradient boosting works and how we use gradient boosting in order to kind of improve. So gradient boosting is kind of a gradient descent method as well, but it is customized or used with random forests with decision trees. Then we'll look at support vector machines. The k nearest neighbors, these are all algorithms that are used for training models to do classification. Then we have clustering, which we call um, the unsupervised. So clustering, with clustering, we're able to group, you know, um, the training data or the samples based on their characteristics and features. So let's just go straight to it. So I've already talked about sklearn, so I'm not going to go through this again. And so we want to talk about regression and classification using decision trees and random forests. So first of all, a decision tree is a model that is structured like a tree, right? So what it does is it splits the data based on feature thresholds. So you are going to essentially think of it like a flow chart where a decision chart, that's why it's called a decision tree. It's a flow chart, and in most situations, you have nodes. At a node, you have a split into either one or two. So if you want to do like if it's a binary tree, you're trying to solve a simple binary decision-making problem. At each node, you only have two choices, right? Either do or don't do, right? So when you have built your decision making based on the tree, at the bottom, you will have the outcomes, right? So the outcome at the bottom is determined by the sequence of choices or situations that arise at each node. So with that, you you use it. Basically, it's mostly used for classification problems where you want to be able to decide on where to bucket something based on a set of questions that are hierarchical in nature, right? So decision trees are easy to interpret. They're prone to overfitting though. So there's something we call pruning where you take out some of the nodes from the decision tree. And, the essence of that is so that you don't have too much representation of a particular outcome, right? Because if not, you end up overfitting. A random forest is now an improvement over the decision tree, right? Using what we call an ensemble. So you take a lot of decision trees and you train them on different subsets of data and features, right? So you have lots of them. Ensemble is when you take a lot of different models and you kind of put them in parallel, like a committee, that then makes a decision. So the ensemble, because it's many, the biases that are associated with, one or individual specific decision trees would be removed kind of, or would be evened out because you have a lot of different decision trees with a lot of different biases. Okay, so those biases get evened out. So that's basically what a random forest is. So a random forest is basically a forest of trees, a lot of trees. So one of its main advantages is that it reduces overfitting, and therefore it helps with generalization. It improves generalization. Um, so we are going to look at all of this in detail. Then we have gradient boosting. So gradient boosting is a method that you use in random forest where you are building trees sequentially. Each new tree corrects errors of the previous, right? And it often achieves state-of-the-art results in tabulator. Okay, so all of the methods that we use, to deal with simple, I would say relatively simple data sets, right? Where you have correlation and it's really about prediction. So those are the ones we are going to look at that as well. Then we also have support vector machines. So a support vector machine basically uses what we call kernels to construct what we call hyperplanes that best separate classes in feature space. Support vector machines are effective in high dimensional spaces, and they use what we call kernel functions, right? So a kernel function is a function that you would use, you have polynomial, RBF, and so on. So uses of support vector machines include text classification and image recognition. Then we have the k-nearest neighbor. So k-nearest neighbor is an algorithm that you use to classify based on how close nearby samples are together, right? So it optimizes that distance between samples that are similar, right? And at the end of the day, it trains. So you have samples that are nearby based on the labels will be classified together. So it's simple, it's easy to interpret, and it uses a distance metric and the value of k, which is a constant that comes out of the training. So example of where you would use k-nearest neighbor would be in recommender systems and in pattern recognition. Then we also have what clustering and dimensionality reduction. So for clustering, basically this is a way of grouping samples together, partitioning them into clusters based on similarity. So it is unsupervised training in the sense that you don't give the the model training targets, right? You don't ask the model the answer should be 1 or 0, or the answer should be, this or that. You basically give data and the model has to find a way to group the data together and minimize the distances or the variances within a cluster. In other words, where it starts off by having actually no correlation between elements, but it begins to train the weights in such a way that the samples begin to come closer and it reduces the variance within a cluster. So you end up over time, you find that the members of the cluster become closer and closer to each other, but the clusters begin to come apart, right? So you start seeing the clusters um, you know, um, work themselves out and become more defined. So the k-means is used for clustering. Then dbScan is also used for clustering. So dbScan, the full meaning of that acronym is density-based spatial clustering of applications with noise. So it groups the points based on density, it identifies noise and arbitrary shaped clusters. And it doesn't require you specifying k, the constant, beforehand. So that's clustering. Then dimensionality reduction. So dimensionality reduction is another kind of problem that you want to solve with these machine learning models. So in most cases, you can have data sets that has multiple parameters, right? Or independent variables. So remember when we're talking about, for example, linear or logistic regression, we talked about doing that with multiple um, independent variables, x1, x2, x3, and so on up to xn. Now, if you were doing y equals mx plus c, it's easy for you to plot a line graph to see the relationship between x and y. If you have two x's, x1 and x2, you can easily even plot a three-dimensional plane, right? And I know a bunch of people did that in their Jupyter notebooks. So in that three-dimensional plane, you can also see the relationship between x1, x2, and y, or x, y, z. You know, you have x, y, z axis. So that's the highest that as a human being you can visualize. Now, if I had three independent variables, x1, x2, x3, it is now difficult for me to incorporate those three in a plot together all in one place, right? Some people did that by separating it and plotting each of the variables independently, but that doesn't give you a full picture of it, right? It only gives you one plane, one dimension of seeing the relationship. It does not give you everything. So now with dimensionality reduction, if you have a lot of planes or a lot of dimensions, a lot of independent variables, a lot of coefficients, all of these basically mean the same thing. That is, the number of x's is more than 2, right? It's from 3 and above, 4, 5, 6. And if you want to still plot and visualize it, right, then you use what we call dimensionality reduction. So effectively, what you are doing is you are adjusting the parameters in such a way that you end up with you kind of adjust um, the parameters in space, kind of, to maintain the relationship, but in a way you figure out which of these parameters has the highest, um, you know, um, should I say relevance, or has the highest effect or impact on the independent variable, which of these independent variable rather has the highest impact on the dependent variable. So you now pick the top three, right? And then you can plot it in the top two rather, you can plot it against the y in a three-dimensional graph. So that gives you a much better idea. It's not perfect. When you do dimensionality reduction, what you are doing is like the best um best case or best effort to see how the you know how the independent variables are affecting the dependent variable. So I'll try to see how to demonstrate this, with visualizations. Visualization is really the best way for us to understand a lot of these things. And I'll also encourage further reading on all of this. So now let's talk a little bit more about decision trees. So essentially, decision tree is supervised learning. And what we have there is that you have a data set where you have X values and Y values, right? You have one X and one Y. So just like what we did with the simple linear regression or a simple logistic regression, right? So and as you can see here, the X with I superscript refers to a single data point, right? So you have X, Y values on a graph, and there are N of them, right? That's what this means, basically. You have a data set made up of pairs of X and Y values, which can be up to N, from 1 to N. So I starts from 1 and goes all the way to N. So you have N pairs of X, Y values, right? That's what this part means. Now, for each value of X, right? X is an element of a real number, right? So that's what this R means. It's a real number. And P means it is categorical. That is, it's probabilistic. So probabilistic means Um, it contains categorical features, right? And a categorical feature is a feature that is not continuous. So let me explain. If you have a feature that the values can only be a particular set of, or the value can only be a subset or a single item in a particular set of values, right? That's categorical. So just use examples. A feature like gender is categorical because you only have a subset of values that you can take from that, right? Male, female, others, or whatever, right? So that's a categorical feature. Another example of a categorical feature would be something like um maybe nationality. So nationality, you say you are Nigerian, you are American, you are, whichever country, you are Canadian, you are Kenyan, you are Rwandese, or there are a limited number of possible values. That's what categorical means. So there aren't an infinite number of countries. There are just a limited number of countries. And I could actually list all of them, and people belong in that. So we have categorized people into that. So any feature that is like that is categorical. Now, a feature that is not categorical is continuous. So for example, your age is actually a continuum, it's in a continuum, it's a number. Even though we have bucketed the number, right? And say, okay, I'm 5 years old, I'm 50 years old, I'm 47 years old. And it looks like we are bucketing it as integers, right? But that's not actually the truth. The truth is your age is in a continuum. So you're not really 47 years old. You are more like 47 years old, 6 months, 2 weeks, and 3 days. And you can even count the hours, minutes, and seconds as well, if you know exactly the second, you know, at which you were born. So it's not categorical, right? Even though we can bucket it, right, and pretend it's categorical, right? So another thing that is not categorical is your height. So if we are saying, okay, the height of students in a class, or something like that. It's not categorical because you have people who are 5 feet 6 inches, those who are 5 foot seven, that 6 feet 11, 6 feet two, even the 2 inches is not exactly 2 inches if you were to measure it precisely. So those are non-categorical. So in decision trees, you typically are going to work with features that are all categorical. If you have features that are not categorical or are continuous, you cannot use them in a decision tree. And if you had to do that, you would have to bucket those, right? So you have to kind of split them into buckets. The same with bucket H and other things. So each element of X has to be a categorical feature, and then each Y is the label or the target value, just like everything else. So if you are doing classification, that means the label Y is also categorical and can be in any category, and the number of possible um, you know, categories, or the number of possible values in that category is between 1 to k, right? But in most cases, classification is only has two, right? Potential values, either true or false, is or isn't, yes or no, 0 or 1, right? So that is typically classification, like we've seen already. Regression, in this case, just like what we looked at, regression means that the value of Y can be a real number. E in this case means an element of R. R means real number. So Y can be any number basically, and it's continuous. So if you are using the problem, if the problem is a classification problem, that means you have categories or classifications of the Y. But if it's a regression, then you have um, real numbers, right, of the Y. but the x's must always be categorical. Now, your goal is that you want to learn a function f of x. So remember, a model is basically modeling a function that when you pass in a given x, it will predict or it will give you a given y. So you're going to train the model by adjusting the parameters, the weights, the coefficients, whatever name you want to call it, until for every x that you used in your training set, right, the y will correspond with what you have given to the model as the label. So of course, this is a standard problem formulation for all machine learning problems, right? And you expect that this prediction of y should be with low expected loss. In other words, the difference between what the model is predicting and the actual value should be as small as possible. So, so what is decision tree? It partitions the input space into what we call axis aligned regions. And then it assigns a prediction, either a class label or numerical value to each region, right? So it is a sequence of yes and no questions, right? That's really what makes a decision tree. It is a sequence of yes and no questions. And if you basically look at it that way, then you see that it's really simple and you understand why it is called a tree, right? You understand why it's called a tree. So um now internally, right, you have it's made up of nodes. So essentially the input space, um the inputs come in and then you have nodes, right? At every node, you make a decision, whether based on the category of the input, right? Based on the remember the inputs are categorical. So based on this category. So let's assume we're using a binary category that uses binary tree, right? So you are going to say, okay, if it is this, right? Or that, if it is this, you go this way. If it is that, you go this way, right? So the internal node will test a feature and check if it matches a particular criterion. If it matches that criterion, then you would now categorize it one way or the other, right? And like I said, the value of X, right, is an element of A or B, can be either A or B for categorical. But for numerical or continuous values, you have a threshold value that you use. Then when you have gone through each of the nodes, you will arrive at what we call a terminal point or a leave, right? And that leave, your value will be decided by all of the nodes. So the best way to do this, right, is for me to do an example. Okay, so let me bring up a whiteboard and okay. So let me just so this is a thinking. Let's assume that you have some sample data sets that is like giving you climate data. Okay. So let's assume the climate data is used to correlate kind of, okay, temperature, um, so for you to predict that the probability that there's going to be a rainfall, right? You have temperature, you have humidity. Okay, so let me just put that down. So you have temperature, you have humidity, right? And then you have well, let's just use this two. Okay. Okay, let me add one more. Temperature, humidity, and the month of the year, season. Maybe we can call it season, right? Season. So let's assume we use the 4 seasons of the year, right? Um, yeah, and then you want to predict whether it rains. So it's a binary classification, and you have two values. Yes, it will rain, or no, it will not rain. So these three make up the X, right? The three features that make X. So you can say this is X1, this is X2, and this is X3, right? So you have those three features that make up your X. And then, of course, whether it will rain or not, that is Y. Okay, so this is Y. Right. Now, in a decision tree, right, you start by checking, you can check each of them. So you can start with season, for example. So that's the first node. And in this first node, you say, okay, um, let's say we take 4 seasons. There are 4 seasons, right? So you have um winter, autumn, summer, and spring, right? Or if it is in Africa, you have just dry and rainy season. So okay, let's go with the African example because it's much easier. We only have to look at two. Well, we also have Hamatan, I guess. So maybe we can say there are three. So you have a dry season, right? You have the Hamatan season, and then you have the rainy season, right? So this is the first point where you have categorical. So that's X3. So this will be X3, right? The node that corresponds to the season. So if it is dry season, then the next question will be what is the temperature? Or is it humid or not? Okay. So I'm not going to say what is the humidity because that is going to give us a continuous value, right? So we are rather going to say, is it humid or not? Okay. So if it is humid, and how do we know, how do you define what is humid? That's where we use a threshold. So you can use a threshold value for humidity and say, okay, if the value of humidity is greater than a certain value, whatever the number is, this could be anything, right? So if it's greater than this, then it means that, yes, it is humid. So you can say, yes, it is humid. Let me use ones and zeros in this case now. So that means, yes, it is humid. And then this is what? No, it is not humid. So if it is humid, then you can do the last check with another feature. Is the temperature high, right? Again, remember it's categorical. So if the input feature is not already categorized, you use a threshold. So we can also decide what is a threshold temperature that you use to consider whether it is hot or not. So maybe let's say, okay, 34 degrees centigrade, right? So if it's 34 degrees centigrade, then again, you have yes and no. So if it is above, then yes, for this specific data set, for this specific data point, right? Yes, it is above, and no, it is not. So in this situation, you have tested the three um, parameters, right? Each test is on a node. So this is what we call the node, right? So you test, then based on this, you test the next one. So this at this bottom, we have finished the testing. There's no other thing. So I have to now decide, okay, based on these three conditions, the value, what was the value of Y? Did it rain based on this condition? If it rained, then you can say Y is 1. That means it rained. Okay, so this is Y now. But if it did not rain, then that means y is what? 0. Now, we've only done one leg of the branch, the other leg. So, for example, in this situation now, x2, this x2 is a situation where dry, it is dry, right? Sorry, it is a dry season. Yes, it is dry season, but the temperature is not greater than 5, right? The temperature is less than, sorry, not temperature, the humidity. I use T, so it's now confusing. So, but I was using T to mean threshold, the threshold for humidity. But yes, so X2 is humidity. So the threshold, um, let me just use a greater sign, greater than, a certain value, right? Let's say greater than T. T is the threshold. So if it's greater than T, this, but on this side, it means it is not greater than T, it's less than T. So you still test the last one here. You still test the temperature. Okay. So yeah, again, this is greater than this. So you test the temperature. Is the temperature greater than the threshold? So you can still use the same threshold as we used here to mean, was it hot? If it is hot and not humid, okay, then this is the case where it's hot, but it wasn't humid. And this is a case where it was not hot and it was not humid. And then you get back to the leave note for this again. And you say, oh, did it rain or not? If it is true that it rained, then you give it a 1. If it did not rain, you know, you give it a 0. So that's for dry season. Now you go to Hamatan. So if the season was Hamatan, so you basically are going to expand this tree in the same way. This is X3, the season node. This is X2, the humidity node. And this is X1, right? The temperature node. So this will result in expansions where you will have all kinds of values, right? At the leaf node. These values correspond to the value of y when this combination of conditions were true, right? So in this case, here would be the value of y. It could be anything. I'm not going to write values here, but it could be anything. It could be zeros or ones. This could be 1, 1. This could be 0. Basically, it means that it rained, right? It rained when uh, during the Hamatan, when the humidity was high and the temperature was high and the temperature was low. So you basically would just break this down that way and you keep on expanding this. This is what we call a tree. So when you hear of tree, that's why it's called a decision tree, because effectively what is happening is that we are making decision based on you know the outcome of the questions that are asked. So at the end of the day, you have this bottom here, which we call the leaves. The leaves correspond to what actually happens, the actual value of y. So with this, now you can then use these values to kind of, you can then begin to train the models, right? Based on the parameters that you train, we're going to look at how they will be trained and so on, so that you likely adjust thresholds or weights and so on, so that at the end of the day, this should be able to give you it should match the actual value, based on the combination of situations. So that is what a decision tree is. Another example would be, okay, if you decide to go to market. So let me give you another simple example. Okay, should I go to the supermarket today? Right. So let's say you are just looking at 2 or 3 conditions. Condition 1 could be, okay, do I have money? If you have money, then so the first node, the question is, should you go to the market, right? The first decision will be, do I have money? In other words, is my money greater than 0? If it is yes, I have money, then you go to another node. If it is no, you have already arrived. In fact, if the answer for this one is no, you've already reached a leave node. So you don't even need to expand any further. You can already say, okay, here I'm not going to the market because I don't have any cash, right? Then at this point you can say, okay, is the shop open? Is the shop open, right? If the shop is open, then of course, the answer would be, if the answer is no, then again, you are not going to go, right? Because the shop is not open, so you're not going to go to the shop. But if the answer is yes, either yes or one, then you can have another decision node again here where you can decide, okay, um, do I have a right, so that can be another decision, right? Or is it sunny? Or is it raining? Okay, so let's use that as an example. Is it raining? If the answer is yes, it's raining, well, can I get transport? Yes, it's raining. Can I get transport? If I can get transport, so let me draw that again. So you can have another decision point here. So this one is it raining? If it is raining, you have two options. No, it is not raining, or yes, it is raining, right? So if no, it's not raining, then yes, okay, I'm going to the shop, right? No problem. But if yes, it's raining, you can still have another decision point where, do I have a transport? Do I have a car to take me to the shop? If the answer is yes, I have a car, then I can still go to the shop, right? So here will be one, right? But if I don't have a car, I could decide, okay, I'm not going, I'll stay behind because I don't want to be beat by the rain. So this is another, simple example, when we talk about decision tree. And this is why it's called a decision tree, because it's basically a way for you to make decisions, right? You are making the decisions by, at each node, you look at the conditions, and if it matches a certain, criteria or category, then, you go one way or the other. So by the time you go through all of this, then you have this, and this is why it's called a decision tree, and it's used basically for machine learning. So let's keep going. So now, so that's the idea, right? The idea is that you build the tree by what we call recursive binary partitioning. What I just did right now is recursive binary partitioning. Basically, and that's what they mean when they say you are partitioning the space, right? We can go back to that, because if you look at the original definition, it says it partitions the input space into axis aligned regions. So this is very, you know, um, this is basically mathematical speak and jargon for what I just did, right? The input, you partition it, it's either yes or no for one particular feature, and then for the other feature again, yes or no, and you do that combination, right? In some cases, once you have classified it, the answer is immediately apparent, so you don't even need to go further, right? But for some other situations, the answer still depends on another decision down the line. So you have internal nodes. This is what I was, the internal nodes are the those nodes where you make decisions. And like I said, if it is a numerical value, that x, if the x that you are testing at that point is a numerical value, then you use a threshold t, a value to determine which way you should go, right? Is the temperature greater than 34 degrees? In this case, 34 degrees is the t, that's a threshold. If it is greater, then I should go outside, right? Um, if it is not, then I should stay inside because I don't want to get cold, right? But if it is categorical, if the values already exist, right, and are not um, tied to, they're not numbers, then you can just use the category. So for example, is he a man or a woman, right? So you don't need a threshold in that case. So then the leaves are the terminal regions. That is the bottom of that tree, right? It's actually an inverted tree. because at the bottom is the leaves. In a normal natural tree, the root is at the bottom, right? And the trees are at the top. But in these trees, in these mathematical trees that we talk about, the root is at the top, which is the first node that we start from. And you see there's just one, while the leaves are at the bottom, which is where you arrive at. So you actually see that, yeah, those are the terminal regions, and that holds the predicted output. In other words, the value of y, right? Which most of the time would mean the classification, I want to go outside or I don't want to go outside, right? But it could also mean a number, right? So okay, so that's basically it. So the core idea is to build a recursive a tree by using recursive by top down is what I just did. I started from that. You must explore every possible um situation, right? That's what greedy means. You don't, unless you are completely sure. Like in the case of, I said, should I go to the supermarket today, right? And we had to, the first variable that I'm considering, the first independent variable is, do I have money or not? Yes, if I have money, then I go, right? But if the answer to do I have money is no, I don't have money. So that one that's the end of it, right? I already have a result from that. It's already um predicted. We already have the prediction. So that's that one. There's okay. So so always you build a tree by recursive binary partitioning, top down and greedy. And I was saying that greedy means you have to explore all the options at each node. You don't ignore any option unless the outcome of following that option is very clear, right? So you don't even need to. But in most cases, if you are using it for regression problems, right, you typically have to be greedy, basically explore the outcome of each. So number one, you start with all the training data in the root. You start with all the training data in the root. And so you start with the training data in the root. Okay. Then for the current node, which is the root node. So it's an iterative process. That's why it's called recursive. You keep going down, down, down. When you get to the leaf, you come back up. So it's an iterative process. So for the current node, you consider the candidate splits, which is basically for a particular feature, J, right? And a particular threshold, what are the possible splits? If you are looking at a binary split, right? A binary split would mean it's either this or that, right? There are only two possible values. So it's either I have money or I don't have money, right? So that's a binary split. But you could also do more than a binary split. You can have a 5 category split. So a good example of where you could use threshold to do multi-category split would be age. You want to classify people into age groups, right? So you would have a baby, you would have toddler, you would have child, you have a teenager, you would have young adult, you have adults, and then you have a senior, right? So each of those are like 6 or 7 categories, right? So what are the thresholds you would use? You say, okay, if it is less than 1 year, then it's a baby. If it's more than 1 year but less than 2 years, then it's a toddler. If it is more than 2 years but it's less than maybe 12 years, then it's a child, right? Or maybe toddlers can be up to 3. Then above 3 years but less than 12 years is a child. Then above 12 years but less than 18 years is a teenager or a teen. Above 18 years but less than 30 years is a young adult. Then above 30 years or less than 50 years or less than, 50 years, 55 years, 60 years is an adult. Then above 55 or 60 years is a senior. So those are now 5 thresholds. So for that current node, you would then consider the split. So you have to split. And then you would now classify that particular data point. So remember, you are doing this for each training data, right? So if you had n training data points, right? So for each of those data points, you have to decide where you will partition it, whether you're going to put it in a baby or senior or whatever, right? So that's step 2. Then for each of those candidate splits, you will now compute a score, right? That score is a score of how much that particular split reduces impurity or loss. So this one also has a loss function, right? So that's the third thing. Then when you have computed the score, right, you now choose the split that maximizes the impurity reduction, right? Or equivalently, that minimizes the weighted impurity of children. So there are formulas to do that, right? Then when you have done that, if that requires adjusting child nodes, you can go into child nodes. The child node is the next one down, right? The next node down from that parent node. Okay, so those are some of the terminologies when you are talking about trees, right? So if you have, for example, this you have this as your node, right? This is a node, and then this would be considered a child node, and this would be considered a parent node. Of course, the root node is a root node is a node that doesn't have a parent. Therefore, is a parent node at the top of the hierarchy, right? Of course, children nodes can also have their own children nodes as well. So it goes like that. But the root node is the node at the top that doesn't have any children. So I'm just clarifying the terminology because essentially when you come to random trees, decision trees, random forest, we are using tree data structure. And I should have probably done that first, but we didn't have a lot of time. So I'll just, try to clarify some of the terminology. While we are at terminology, let me even also help to clarify when we're talking about trees, you have, yes, like I said, this is the root. The root is the node that doesn't have any parent. Then you have children, right? So this root node has 2 children. This one may have 3 children, right? And then you now have this connection from the root to the child is what we call an edge. It's called an edge. While the point of decision is called what? A node. So whenever you hear of node, right? This is a node. This is a node, right? This is a node, right? Then at the bottom of the tree, you have nodes that don't have any children. A node that doesn't have a child is called what? A leaf, right? It's called a leaf. So when you hear this terminology, that's typically used in tree data structures. So let me just so in case you hear all of this. So now when we talk about impurity reduction, we are going to look at some of the algorithms for that. So recurse on each child node until a stopping condition is met, right? The stopping condition can be you have a pure node, you can have minimum samples, you can have max depth, and so on. And then optionally, you can prune, right? Pruning means you chop off some subtrees or some nodes and all the children and grandchildren and great-grandchildren of that section, right? So that to minimize overfit, but also because if to kind of optimize the process, right? So this is what we call a greedy algorithm because it picks the best immediate split without backtracking, right? Um, so that is kind of the basic principle. Now, if you want to do classification, either binary or multi-class, binary means you are classifying between true or false, is or isn't, yes or no, and so on. But multi-class is you are classifying between multiple, members of a class. So you are classifying between maybe, um, I am Nigerian, I'm African, European, or that, where you have multiple classes. So in each of either case, right, this is the function. You have what we call entropy. So entropy is calculated using a log function. Log function pk, where p is the probability function, right? It's the proportion of class k in set S. So what this means basically is that um, at the particular node, when you're at a particular node, so let me again try to clarify this. When you're at a particular node, um, so you could have, let's assume that this set, if you know set theory, right, represents the set of values. So let's go back to the example that we were using. For example, we want to the rainfall data, right? We had X1, X2, X3 as a three possible features that we're looking at. And then we also had each of them representing a you know a condition. So let's take X1 as we started with X3. So let's take X3, right? So let's take X3. So if you recall, X3 was talking about the season, right? So now, if you look at this is a sample population, right? Well, you can call it sample, right? Or population. So this is the set S, right? That we are talking about. So when we say set S, right? This is the set S, and this has values. So let's assume you have 10 data points. We took 10 data points of rainfall data, right? And at each point of the rainfall data, so we would have, remember I used the superscript I to represent each data point. So now let's assume that the season data, which is X3, so the season data for the first data point was that we have Hamatan. It is Hamatan. This one is Hamatan. Maybe you have out of the 10 data points, right? 5 of them are Hamatan, season is Hamatan, while 4 of them, or 3 of them, season is dry, right? And 2 of them, season is wet or rainy, okay? So DD, and then 3 of them are dry, and then wet, or let me use W for wet, so this is 10 data points, right? So if you look at this now, PK is a proportion of class K in the set S. So for the class that represents Hamatan, let's call it H, okay? The PK for H, right, which I can call PK comma H, is what? Is the proportion of H in this set, which is what? 5/10, right, or 0.5. So similarly, for the set of D, which is the dry season, right, the proportion of K in this set, which is the proportion of PK, the proportion of dry season, is what? 3/10, which is 0.3. Same thing with wet season, right? So wet season, the PK for wet season is 2/10, which is 0.2. So that is a proportion. That's the PK. So for each data point, you're going to do log of PK to base 2 times PK. So there are 10, um, there are 3 classes. So K here refers to, right, so take note that K here refers to the number of classes, right? Number of classes in the category, right? So in this season category, right, there are 3 classes: harmattan, dry season, and wet season. Now, similarly, so you basically are going to do HS, which is the entropy. So for this one, the entropy, you would calculate the entropy by for each class. So we'll have 3. So the HDW. So for H, that means the entropy for H. Oh, now there's a bit of confusion because the H for harmattan is going to confuse us with the H for entropy. So let me use a different alphabet for harmattan. What do I use now? Uh, well, let me just use T. Let me just use T, right? So let's say T, which is a harmattan. So the H, right? The entropy, right, for the entire set will be the sum of the entropy for each of these, right? Um, so let's calculate the entropy for T would be, the entropy for T would be 0.5 log to base 2 of 0.5, right? And the entropy of D, this is T, and the entropy of D, I can call this HT, I can call this HT, and I can call this HW. The entropy of D is going to be 0.3 times log to base 2 of 0.3. And so on, the entropy of W will be 0.2 times log to base 2 of 0.2. So I'm just trying to explain what this means. So if you do this maths, well, we can do this quickly. Log to base 2 of 0.5, I can actually come up with that. That is um, um, 0.5 is 1/2, which is 2 raised to the power minus 1. So that's minus 0.5. Log of 0.3, I can do a quick calculation. But anyway, we are going to do all of the maths in a Jupyter notebook very soon. So when you then sum, so let's get a value for this. I guess I can bring up my calculator and do this real quick. So log to base 2 of 0.2 of 0.3 times 0.3. So this will give us 0.36. So this will be minus 0.36, or let's just say minus 0.4. Okay. Then same thing with this log to base 2 of 0.2 times you know um so that this will also be minus 0.32, minus 0.32. So when you add this together, this will give you about 1.22, right? Minus 1.22. So you can see this has a negative sign because we are taking log of fractions. So we would, of course, yeah, so we would, of course, then negate it, as you can see. So after taking the sum, we'll negate it. So we're actually going to get the entropy, in this case, to be 1.22. So we would do that. And then similarly, we calculate information gain, which is delta H, which is the difference, the change in entropy, right? The entropy minus the fraction of the entropy for each split, the split to the left side and the split to the right side. And then we'll do what we call Gini impurity. The Gini impurity is the sum of the square of the partition proportion, right? The pk, right? So the sum of the squares subtracted from 1. So that gives you Gini impurity. So when you reduce the Gini impurity, um, that means it is information gain. So these are the 3 parameters that you calculate: the entropy, right? The information gain, and then the Gini impurity. Okay, so once you do that, then the next thing is, this is for classification. Now, if you are doing a regression type of problem, you will now do, you have mean square error, which you can use as well. So mean square error is a standard thing, right? Which is, y hat, y minus y hat, right? In this case, y hat is the mean target in a particular node, right? Based on the split. So again, choose splits that reduce weighted mean square error. So what do you mean by split? I'm sure somebody will be asking all of that. So what is split? Basically, it it means when you sort the values. So again, remember, for each feature, you have a category, and the category has number of classes. So you now, if you're using midpoint, if you're using threshold rather, um, most of the time what you're doing is that you are adjusting the threshold, right, to determine the split, right? If you're doing a numerical regression, you're adjusting the threshold. So for example, what you'll be doing is adjusting which threshold should I use to determine what is, high temperature or not. What threshold value should I use to determine what is high humidity or not? Because the threshold determines how many goes into one side and how many goes into the other side. If you increase the threshold, less will go into the zero side and more will go into the zero and less will go into the one. If you reduce the threshold, more will go into the one and less will go into the zero. Or anything, it depends on the data, and it also depends on the characteristics of the data. So the whole idea is that for each numerical feature, right, you can sort unique values, consider thresholds to be at midpoints, right, between consecutive unique sorted values. So you can look at this, for example, a threshold could be the midpoint between the X for 2 different data points, right? X at K and X at K plus 1, right? So remember, the K refers to the classes, right? So you can choose at any point where you want to split it, right? Based on sorting. So that's how you can split for numerical features. For categorical, that has few categories, you can actually group the categories and partition for binary, um, or order them by target statistic and then treat them like numeric. So you have to find a way to do binary partitioning of categories. So yeah, then you have what they call stopping criteria. So stopping criteria is minimum samples per leaf or maximum depth, number of splits that yield meaningful impurity reduction. And then pruning is when you can cut down a tree, right? and by chopping off sections of it, mainly because of overfitting, right? So you remove a node and all the succeeding children and grandchildren from that node, in order to basically reduce overfitting. Because if the nodes are too many, you have overfitting. Overfitting always happens when the size of your model is much bigger than the data that you have. So you have complexity. Complexity, this has to do with how fast
Meanwhile, huh?
your model
What?
and how fast your model would would converge, So I won't go into that. So this is like a very simple example of using a decision tree. So you have a data set of 4 points, single numeric. You have a feature X, which is this, and then you have a label Y. So this is like a very simple problem just to, show us what it looks like. So this is the feature X, and it has 4 values, 4 data points, 1, 2, 3, 4, each I, and then you have Y. So it has also 4 labels. So if you want to do this, of course, if you're using simple normal linear regression, it will be very easy, or logistic regression. Now, but here, what we are saying is the first thing is you have to ask yourself, what are the possible thresholds that I can have? Should I have a threshold at 1.5? If I have a threshold at 1.5, that means I'm going to split, right? I'm going to split it into 2 buckets, right? Above 1.5, so these 3 will be in that bucket, and then below 1.5. So this is one way of splitting. The second threshold, you could say, okay, I want to split at 2.5. So if you choose to split at 2.5, similarly, then you will have this as your split point. And then the first bucket would be this, and then the second bucket would be this, right? And you could also decide to split at 3.5. So these are the considerations, right? When we're talking about splitting, choose where if we decide to split at 3.5, then it means that the 0 bucket will be this and the 1 bucket will be this, right? So now if you look at the parent node, you have 2 zeros and you have 2 ones, right? For the labels, for the leaf nodes. Then the class proportions for P0, right, is 0.5. For P1 is 0.5. The entropy, so let's assume we actually did it that way so that we would have, this is assuming we split at 2.5, right? So if we split at 2.5, then you have, we have 2 values for P0 and we have 2 values for P1 for the 2 classes. So if you have 2 values for P0 and you have 2 values for P1, then of course P0 will be 2/4, which is half, 0.5. P1 will also be 2/4, which is half. Okay. The entropy will now be the sum of P0 log P0 and P1 logs P1, right? So P0 log P0 is 0.5 log 0.5 plus 0.5 log 0.5 again. And of course, you apply the minus. So like I said, log of 0.5 is -1. So you have plus 0.5 plus 0.5, which is 1, right? So that is the entropy. Then the Gini would be based on this, which is 1 minus the sum of the squares of the p's, right? The pi's. So sum of the squares of 0.5, 0.5 squared plus 0.5 squared is 0.5. 1 minus 0.5 is 0.5. So that gives you the Gini. So now that is if you consider threshold of 2.5, like I said. So you split the threshold 2.5, you will have left, if x is less than 2.5, you have items 1 and 2, like I have said. And the labels are what? 0, 0. And the labels are pure. So here, pure means that there is no there's no inclusion of a label that does not fit. Because remember, we said we want a split point where the outcome, the prediction is, if it's above this line, then it should be 0. Below this line, it should be 1. And this split point gives us a perfect, separation. So with this, what it means is that, yes, the labels are 0. There's no 1 here. So it's a pure um, split. Then the entropy, HL, like I said, is 1 bit. Okay. Um, and then the Guinea is 0. For right, the right is down, basically. Because when you say left and right, that's from the standpoint of the node in the tree. Remember, we go left and you go right. Left is normally when it's above, so that's the 1. Then right is when it goes, sorry, the other way, left is when you go below and right is when you go above. So for right, you have items 3 and 4 again, and the labels are also 1 is also pure because there's no 0 here. Everything is ones. So again, entropy HR for the right, the entropy is 0 and the Guinea is 0. So um, from this, weighted child entropy is 0, information gain, which is this 1 minus the child entropy, 1 minus 0 is 1. Guinea reduction is 0.5. So the best split is at 2.5, producing 2 pure leaves. The 3 perfectly separates the classes. So if you had noisy data, leaves would not be pure, and you you would it would make sense for you to continue to try to separate by adjusting the threshold more. Okay, so so that's our countries. I know a lot of these maths may not really, unfortunately, we don't have time to really dig into it. So we'll just use sklearn and use decision trees. You don't need to worry too much about the maths. I just wanted to go through it. So what are random forests? If a random forest is, like I said, an ensemble of decision trees. So like we said, the decision trees will not be very, very um, useful because they tend to have biases, right? So what happens is that we now build multiple decision trees based on randomness, right? So that the trees are roughly independent, right? And the predictions can be aggregated. The thresholds are selected at random, right? That's the whole essence of it being called random forest, right? At each point, at each decision point in the node, you now choose a random threshold. So as you choose random threshold, the tree is going to have a different behavior. So what we now do is we now pass the same information through all of those trees and see what the prediction is, what prediction comes out of it, right? And based on the prediction, for classification, you take the majority vote of the trees, right, as the output. And for regression, you take the average of the tree predictions. So why this helps is the single trees have low bias but high variance. That means they can easily overfit, right? Low bias in the context of training of machine learning models, bias is really has to do with the um, inbuilt misconceptions or wrongness of the model. While variance, we'll look at all of this later on. So bias and variance are things that we use to measure how well a model is able to fit the data. So with random forests, you can then average many uncorrelated or weakly correlated estimators to reduce the variance. So random forests reduce variance while keeping bias low, giving much better generalization. So if you want to train from random forest, you have all of this. You have a Bryman's random forest algorithm. For B equals 1 to capital B. The capital B refers to the number of trees. So remember, we now have a decision tree. We have B decision trees. It can be any number. It can be 100. It can be 1,000. It can be 10, right? So you take a bootstrap sample, right, from the training set. That sample has a data size dB, right? And then you train a single decision tree, TB, on that training set, DB, with one modification, right? So the modification is when you are considering a split at a node, you select the best split only from a random subset of M features instead of all P features. So what that means is that um, you only pick. So if you had like 3 or 4 features, for example, if you go back to our Hamatan uh, um, rainfall example, right? So you have 3 features. You have the season, you have the temperature, and you have the humidity. Then you can you can then choose the best split, maybe only from 2 of those features. While the third one, you leave it, as it is. You don't adjust it. You don't train it. That's what I mean. Because training of decision tree is basically adjusting, finding the threshold or split points that gives you the best results. That's basically what training a decision tree is. So when you are training random forest, you do it iteratively. Like you create, let's say, 10 decision trees. For each decision tree, you train it. Okay. But the training is that you are not going to adjust split points in all of the features, right? You only pick. So like when we're doing that um, rainfall example, we had 3 features, and those 3 features led to 3 layers, 3 points of decision making, 3 nodes, basically. Well, more than 3 nodes, because but 3 levels of decision making, starting from the root node, which was a season node, and then the next node where we had to choose the temperature, the humidity rather, and then the last level, which we had to choose the temperature. So we could decide at each point you try to maximize how much the tree is able to predict by adjusting the split point. So now what we are saying here is that don't adjust for all of them. Maybe I can adjust for 2 out of those 3 features, right? When you adjust for 2 of those 3 features, then typically the number that you will choose, the M that you choose, the number of features that you want to optimize is for classification, you use square root of P, right? While for regression, you use P divided by 3. Regression is not numeric regression. So when you do that, you then grow the tree to full depth. So what grow the tree to full depth means is expand the tree like I did. You draw each node and you get it to the full depth. So you do that for all of the trees. And remember, each tree that you take, you are going to train it on a subset of the training data of size n, not all the training data. So that would what that does is that since you are training each tree on a small sample data set, the tree would tend to specialize in that small sample data set. Okay, you now train another tree on another small sample data set, it will specialize on that, and you keep doing that until you have trained all the B number of trees on B different subsets of the data. You now have B trees with different biases, right? And then you put all of them together in an ensemble, and you then use that as your model to predict. That is basically what a random forest is. So when you do prediction for new X, classification, regression, um, so the Y hat, okay, is mode. Mode means the highest value, basically, of for each tree, right? From 1 to B, for each of the decision trees, you pick the decision tree that gives you the highest value. Like remember, we're talking binary classification now. So if you pick the tree that gives you the highest, whether it's a 1 or 0. If there's a single tree that gives you a 1, then that is the prediction. Okay, that is in classification. Or the one that gives you the highest if it is a multi category classification. or multi-class categorization or classification. Now, for regression, y hat, the prediction of a random forest is going to be the average prediction, the average 1 over b times the prediction of each tree. So you take the prediction of each tree and you average it. So that's basically what a random forest is. Basically decision trees that you take plenty of them and let each of them make a prediction for you. Then for classification, you pick the one that you pick the class that the highest number of trees vote for. That's why they say voting system, right? The one that the highest number of trees say, okay, it should be one. So if, for example, you have trained 10 trees, on this weather forecasting, and for a particular data point that you give to it, 7 of those trees tell you that it will rain, while 3 of those trees tell you that it will not rain. It is now saying that the prediction of the entire ensemble of trees should be that it will rain, because the highest number of trees have told you that it will rain, but there will be a minority that are telling that it will not rain. So that's basically how you do classification with random forests. But for regression, you would, if let's say it wasn't to classify whether it will rain or not, but instead to give you an actual value of the amount of millimeters of rainfall. Okay, so you have again 10 trees, and each tree is giving a value of what it thinks after being trained that will be the number of millimeters of rainfall. Maybe this one will say 3, the other one will say 5, 20, and so on. For regression, what you do is you take the average of what all those trees are telling you, and that will be your prediction for the entire random forest. So you will see that random forest is basically just multiple trees that ensemble means when you take the prediction you take is based on what all of the trees give to you. And this is the guideline for, ensembles. So, yeah, bootstrap sampling will reduce variance, what we call bagging, which is being able to sample, subsample, feature subsampling at each split decorrelates a tree. So what this means basically is that you can do subsamples within features, right? So if a few features are very strong predictors, different trees would otherwise all use the same ones and stay correlated. You want to remove the correlation between the trees, right? So you can do subsampling between features. In other words, don't sample the same data for a particular feature, right? Try to avoid sampling from the same data. It's always good to have different. So that's why we say, okay, take subsamples. If you had a data set of 10,000 data points, right? And you have 10 decision trees, then the question is, should I now divide that data set of 10,000 samples by 10? So I'll now sample I'll sample 10,000, 1,000 rather, for each tree that I want to train. Is that okay? Alternatively, the other thing is something we call overlap, where we say, okay, is it just 1,000? Shouldn't there be overlap between the data that I have used to train each tree? There should be some overlap to ensure that there is continuity, in the predictions. Yeah, so OOB is out of bag error. OOB estimate each training sample. For each training sample I, some fraction of trees did not include it in their bootstrap sample. Use those trees to predict Xi and compare to the true Yi. Averaging over I gives an unbiased estimate of generalization error. So this is kind of like cross-validation, where you are saying that find a sample that you did not use to train some particular fraction of trees, right? And use that, right? Use those trees, to predict. Basically, use trees that find a sample of data that some trees never saw in their training data, okay? And use that sample of data on those trees and see if they can see what they predict, right? And then compare it with the true value of Y. Okay, so and then average over that. right? That will give you a way of calculating the performance. That's like a metric to calculate performance of it of the random forest. Yeah, so variable importance measures mean decrease in impurity aggregated across trees or permutation importance. So you can also measure the increase in the out of bag error when a feature is shuffled. So a decision tree can have low bias. Low bias means complex functions it can fit. In other words, the model is huge. Well, I wouldn't say huge, but the model is capable. But it could also have high variance. So that means it is overfitting. So it's sensitive to training sample. When you change the training sample, what it gives you changes, right? So it's basically training, it's learning, it's not generalizing, it's learning only on that training sample. Okay. So bagging or forest averages many high variance models to reduce variance. That's the benefit of using random forests. So if trees are independent and each has a variance of sigma squared, then averaging B trees reduces variance to sigma squared over B. Correlation among trees reduces the benefit. So what this is saying again is that um, if you are having variance, which is overfit among multiple trees. Since each tree is making its own prediction, averaging reduces the error by basically the number of trees that you have in that random forest. So this is a simplified pseudocode of how you can train a tree, right? So you have a stopping condition. If the stopping condition is true, you return leaf, right? And so you now do a best split. Best split is to keep iterating around the threshold value, right? And calculate the impurity reduction for that threshold value. And you keep iterating until you get an impurity reduction that is zero. Basically, impurity has not been reduced. In other words, so remember, a pure split means a split where all the values in a particular class are all there and there's no value from the other class, right? In a particular category. So all the values are zeros and there's no one, or all the values are ones and there's no zero. That's a pure split. So impurity is basically a measure of how impure, that's how many um of the non the classes that don't belong, how many of them are in there. So for example, how many ones are in the part of the class that should be zeros, or how many zeros are in the part of the splits that should be ones. So the impurity reduction is basically when you change the split, how much has the impurity reduced? So you actually, your measurement is not really the impurity per se, but the impurity reduction between this split and the last split that I did, right? So the best split is a split where any other split you do will not reduce the impurity of the best split anymore. Like, it's a best split because no matter any other split that you do, the impurity will either be higher or the same, right? You can't get a lower impurity. So once you get to that point, then that's the best split, okay? And then once you have the best split, you now um, move on to the next feature, right? Which is the next node, and you also train the tree. So you train with um, the left side of the tree and you train with the left node and you train with the right node. And you can see this is basically a recursive function that does that. So at the end of the day, when you've done all of this, you now return a value that represents the best split, and that is how you train a random forest using the cat method. Sorry, not a random forest. This is how you train a single decision tree, right? Using the cat method. Then for a random forest, it's basically you would have a forest, you have a bunch of you have a forest which is a list, a bunch of trees. So for now, there's nothing in the tree. Then you choose a B, which is the number of trees that you want to have in that forest. Then you now do a bootstrap sample, which is basically to bootstrap that tree, right? Then you now train the tree with feature subsample. So in this case, if you are going to train each tree separately using a using a cat method. So when you have finished training the tree, of course, you have a subsample of the data. When you're finished training the tree, you now append it to the forest. Okay. And you keep on doing that for the number of trees that you want to do. So by the time you finish, you have trained B number of trees. Each tree is trained using the cat method. And you know, at the end of the day, you just have that forest as your random forest. So to now do prediction, like I said, with a random forest, you do prediction for each tree in the forest. And when you are done, for classification, you pick the value that was voted for by the highest number of trees. And for regression, you take the average prediction from all the trees as your value. So yeah, so that's basically it. Now, um, we can try doing that, and I think I'll look at that. Oh, we've run out of time, so the other things I would have really liked to look at, but maybe we can look at those next week. But the other things I would really have liked to look at were support vector machines, but maybe we'll just go through them, quickly, briefly, without going in depth. So with sklearn, it's really simple. You just use a decision tree classifier and you run dt.fit. Simple, right? But with random forest, you do same thing. Random forest classifier, you specify the number of estimators, which is the number of um, decision trees that you want to use in that random forest. Then you want to specify other parameters like this, and you just run rf.fit and it gives you your values. So this is basically um, what it looks like. So strengths and weaknesses. So decision trees, the main strength of decision trees is that it is easy for you to interpret um, its predictions, right? It can handle numeric and categorical features. It requires little data pre-processing because you are just using thresholds. So you're not going to have gradients overshoot and all of that. The trees don't actually use, well, okay, so I'm going to back up on that. Trees don't use gradients, right? But there's what we call XG boost, which is a gradient boost, which is used. It's kind of an optimization or adaptation of gradient descent that we use for random forest decision trees. We'll look at that also. Um, but yeah, you require little data preprocessing for trees. You can capture it captures non-linearities and feature interactions. It's very fast in inference because you're basically just in inference when you finish training, it's basically just a series of it doesn't need to do a lot of calculation. The weakness is high variance, like we said, that is it can easily overfit on the data. Decisions are axis aligned. So what this means is that you can't have oblique splits unless modified, and it can be unstable to data perturbations. So what this means by axis aligned is it's always difficult if you have things all mixed up, like your the labels are all mixed up 1010. It's very difficult for you to use um decision trees where there is a lot of non-linearity, even though it does capture non-linearity to a certain extent, right? But if 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 you have like 1010101010, it will be difficult for you to find a split point, right? If you have 1010101010, like where will you find a split point that wouldn't have impurity? and the proportion of the impurity would still be the same, right? So that's one of the challenges with decision trees. Random forests are very excellent out of the box performance because they are combining um, the you know, low bias of a decision tree, but we are using multiple decision trees to eliminate the high variance, right? It's very robust. It can handle large feature spaces, right? If you have features that are up to, I don't know, tens, hundreds, right? It's very easy. It can handle that. It's resistant to overfitting, of course. That's the whole reason why it was designed. It was basically that's why it was designed. And it provides feature importance. So you can actually have some kind of hierarchy on the feature, which one matters most, and so on. And then it has this OOB error. So the weakness is that it's less interpretable because it's an ensemble of many trees. It's difficult for you to say, oh, this is how this forest came by this prediction or this outcome. It has a larger memory or time. It takes more memory, more RAM to calculate if you have a lot of trees, and it takes more time as well, of course, if you have a lot of trees. And it can struggle with very high dimensional sparse data. It's biased when the data has strong class imbalance, right? So what this means, sparse data is when the data is not much, right? And it's high dimensional. In other words, you have very few data points, but you have a lot of features, right? Well, that's the problem for almost any kind of machine learning approach these days. It's also biased when the data has strong class imbalance. So what this means is if classes are not kind of equal or not close to equal in terms of distribution, right? It may have some challenges. A good example would be, okay, if you have data of, I don't even know what example to use, but if you had a category and, you had like two classes in the category, let's say pass and fail. Okay, that's a good example. You want to do some kind of prediction based on the students that pass a particular exam and the students that fail. So you find that the number of students that pass are far more than the number of students that fail. So let's say 90% of the class always passes, or 95%, and only 10% always fails. That is a high imbalance. You have more data of people who are passing than data of people who are failing. So it will be difficult. It's going to have challenge being able to do a good prediction on that simply because of that imbalance. Okay. So the other thing is for trees, the kind of hyperparameters that you would tune for random forest and for trees. For trees, you tune the max depth, you tune the minimal school split, you tune the minimal school's leaf, right? Then you tune the maximum features for random forest because there is remember the features that you are going to adjust or train on in a random forest is not the entire set of features but a subset. Then the criterion that you are going to use to calculate the performance, the cost function, basically whether you're going to use the Gini. The Gini is basically a measure of the loss of impurity, whether you use that or whether you use entropy. Then other pruning parameters. Then for random forest, the number of estimators, which is the number of trees in the forest. Then the other ones, max features, max depth, bootstrap, max feature, max depth is still the same as for the trees because basically that's the hyperparameter per tree. Bootstrap is whether you use bootstrap and whether you use OOB score. So then whether to use cross validation or OOB to pick good settings. So we are going to look at this as well. So gradient boosted trees. So like I said, you can actually use a method of gradient descent to improve how you train your decision trees. So that's gradient boosted trees. You have XGBoost, Light GBM, and Cat Boost as some of the methods that are used. So in this case, you are sequentially building the trees to correct the residuals, right? Then you have extra trees, which is extremely randomized trees. So you are going to choose your split thresholds randomly, right, for that, and then you pick the best among them. Then you have what we call oblique trees, right? So the splits are linear combination of features. So you're not just splitting based on a constant value, the threshold for each of the features, but you create a linear combination of the features and use that. Then how to handle missing variable values. We have what we call surrogate splits, special missing indicator, and then calibration of properties. So I'm not going to go through all of this because there is a lot here. Now, what I would like to do is to do a little example um, with the decision tree and the random forest, just to show you a simple hands-on, simple from scratch, and then do the same thing with sklearn. Of course, sklearn is easy. It's not, if it's sklearn, it's not worth a whole 2 hours, right? So let's see how we can do that. So I'm going to start a new Google Colab, and so we are going to look at the same problem that we solved um, the other time. We're going to basically use the same data and try to do a kind of classification with um, so the first thing is that we will um, let's start off by um, import numpy, and then import counter. Okay, then the first thing we will do is to put together our Guinea impurity function. So yes, Guinea impurity. So remember, Guinea impurity is a way that we will use to measure the is a way we use to measure the um how good, or the improvement, basically a way to measure the improvement of our decision tree as we are training it. So so I just defined the function for Guinea impurity. So let's look at this. So first of all, you do a counter of y, right? Um, so basically this allows is what we this counter is a Python data structure that allows you to count what is inside y, how many things are inside y. So it's called a bag or a multi-set. So when you store the elements, um, you store the elements as the keys, and then the account will be stored as a dictionary. So what that means is that you can actually store, for example, if you store this, A, B, C, D, E, A, B, C, D, A, B, C, D, A, B, C, A, B, A. It's basically you have put in a lot of alphabets or letters there. It will now give you a count of each. So that's the benefit of this. The benefit of the purpose of this counter is for us to be able to know the counts of each of the um from each of the data samples, right? How many are of a particular class, right? So for example, if you put inside this counter, for example, if you put remember the y are the predictions, or the predicted values. Sorry, not the predicted value, the true value. So if you had a y that had maybe 0, 0, 1, 1, like we saw, then this counter will allow you to count. will allow you to count, 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12, 13, 14, 15, 16, 17, 18, 19, 20, 21, 22, 23, 24, 25, 26, 27, 28, 29, 30, 31, 32, 33, 34, 35, 36, 37, 38, 39, 40, 41, 42, 43, 44, 45, 46, 47, 48, 49, 50, 51, 52, 53, 54, 55, 56, 57, 58, 59, 60, 61, 62, 63, 64, 65, 66, 67, 68, 69, 70, 71, 72, 73, 74, 75, 76, 77, 78, 79, 80, 81, 82, 83, 84, 85, 86, 87, 88, 89, 90, 91, 92, 93, 94, 95, 96, 97, 98, 99, 100, 101, 102, 103, 104, 105, 106, 107, 108, 109, 110, 111, 112, 113, 114, 115, 116, 1 It will allow you to count, and it will give you something like this, that for, let me put it properly so that you can understand. So it will give you a dictionary. Well, actually it's a list. So but it will give you something like this, where it will tell you that zero, there are two zeros, right? And there are two ones. So it makes it really easy to you know, track what's going on. So impurity is one. So we start with this value. The total, of course, is the length of all the elements. So for label count in count of items, so remember this is what it is, and it's actually a list, right? So it's going to tell you how many are zeros and how many are ones. So you now calculate the probability. So remember, the probability is how much in each class, in each category, how much of each class. So in this category of Y, how many are in class of zero, that is zeros, how many are ones? So if the total is 4, 2 over 4, that will be 0.5, and 2 over 4, that will be 0.5. So just to test this, right, if I were to run this impurity, Guinea impurity, right, and what I pass in is 0011 exactly, then what you will get is the impurity would be 0.5, right, divided by zero. For the first one 0.5, then the second one is 0.5. So this is now square, which is 0.25. So so this is actually implementing. Let me just put this here. The Guinea impurity is actually implementing this function. It's implementing 1 minus summation of pi squared, right? Is 1 minus summation. So let me put that here as well, um, using latex. So the Guinea impurity equals 1 minus summation of pi squared, right? Pi squared. That's basically what it is. So oh, sorry, this should be a single. That is that's Guinea impurity. So that's what we are basically doing for each I. So maybe I should have done that. Sum for I equals, 1 to n, where n are of course the number of data points. Okay, so sum for I equals to 1, for I 1 to n, right? So that's Guinea impurity, and that's what we are implementing here. So if we have 0011, there are two zeros and two ones, so that is half half. So when you square the 0.5, you get 0.25. You add it to the other 0.25, right? So you are going to get 0.5, and you subtract 1 from 0.5, and that will give you 0.5. So this should actually give you 0.5. That's a Guinea impurity. Now, so after that, the next thing is we do a data set split. Okay, so the data set split uses this formula. Basically, you can decide on what threshold you want to use, right? You decide on what threshold you want to use. So based on choosing threshold, 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 threshold. Okay, so that is the second thing, right? So, but I'll skip this, and then now the next step is to find the best split for a node, right? Find the best split for a node. So the algorithm for finding a best split is you start with a particular feature, right? You take note of the best feature, you take note of the best threshold, and you take note of the best impurity. Okay. Now, the current impurity is you calculate the Gini impurity for Y, which is the current impurity. Then, of course, X has number of samples and number of features. So we get that from the shape of X. Then, for feature in feature indices, so we are going to pass the feature indices, right? Which features that we want to find the best split for. You now get the value, right? You get all the values, which is the unique. The reason why you have to do unique is because this is categorical, so there may be duplications of values of the category. So you just get only the for each of the values of the category, or for each of the classes of the category, right? So you now check for threshold in values. You will do you split data set based on that threshold. And if the length, so you now have X left and Y left, the X right and Y right. X left is the number of features on the left side of the split, which is the lower than the split point or the threshold. Y left is you calculate the value of Y based on that particular X split point. Same thing for Y, X right and Y right. So X right would be the items on the right of the split, right? And then Y right would be the value. So if the length of X left is 0, that is, there's nothing on the left of the threshold, or there's nothing on the right of the threshold, then that means you have reached the end of the selection, basically. But if not, you just keep going, right? You calculate the probability on the left, which is the number on the left divided by the total number. So that's just that probability. Then P right, of course, since this is binary, the P right will be 1 minus P left. So you now use those two values to calculate the Gini impurity. The total impurity will be the number on the left, or the split, the proportion of the split on the left, times the Gini impurity on the left, plus the proportion of this split on the right and Gini impurity on the right, right? And then um, if the impurity, the current impurity is less than the best impurity, then you adjust. So that means that the best impurity is now the current impurity. The best feature is the feature that you use to calculate that impurity. And the best threshold is a threshold, right? And you keep doing that until you get best feature and best threshold. So that's best split. Now you need to do a bit of tree, the you know the tree itself. So yeah, I think this is going a bit deep, but let's just look at it. This is a tree structure. So you need to be able to represent that tree structure, and it's represented with this code. Then the decision tree itself, the classifier, right? The decision tree classifier now will use all of what we have done, right, to do that. So so this is that, right? And then you have a fit function, right? I'm going to share this as an example for us to look through. But this decision tree basically goes through that algorithm that we mentioned, right? That pseudocode, where it keeps going down through each tree, and then it will keep shifting. It will find if it keeps adjusting or shifting threshold until it gets the best threshold that gives you the lowest Guinea impurity score. And then when it finds that, it will use that, so that threshold, that's that parameter for that particular feature. And you do that for all the features and you end up with a trained decision tree. And then when you have done that, you can now do predict with it. So this is just to show you how this looks like if you had to do it all by yourself. Now, I'm not going to go into random forest, perhaps, but I'm going to just drop the code for random forest here as well. So if you want to do a random forest classifier, so remember for random forest, we will actually have to generate multiple trees. And then for each tree, we will then train it on a subsample. And yeah, so we'll train each tree on a subsample of the entire sample set. And that is going to form a random forest. But yeah, you don't need to worry about all of this. I'm just doing this so we can see, what happens under the hood, right? So this is all what is going on under the hood. This is what is going on under the hood. So but thank God for sklearn, right? Sklearn, you don't need to do all of this. You don't need to do all of this. So with sklearn, right? This is how you now do um this is how you do with sklearn. So let's look at this simple sklearn code, right? So the nice thing with sklearn is that sklearn actually gives you um sample data that you can use, right? And then sklearn also does test train split, which we'll talk about, shortly. But look at this sample code. This is basically how you can do regression with random forest. And this is as simple as it gets. So let's break it down. So first of all, we have importing. You're basically importing this in. And you get the California housing data set. Okay. So let's see the X and the Y, which is this will allow you to see the data set. So it's a data set. sklearn has built-in data sets, so you can use that just for learning purposes. So this is a data set for regression, right, on housing prices. So this is feature. These are some of the features, right? Let's look at data itself so that we see how data looks like, which is data is a data frame. So you have this, right? Um, California housing data set, right? And basically it is on the X side, which are the features, it gives you information about the conditions, right, that contribute to cost of housing, while on the Y, you actually have the cost of housing. Then we now do a split. So you have test train split. We'll talk about this more later on, right? But remember, there is this thing when you are training data sets, you have to be able to differentiate the data that you want to use to train the model, right, from the data that you want to use to test the model. Okay? The data that you want to use to train the model is already fit to it. So you cannot use that one to do evaluation. If you use that to do, most models will get a very high score because that's what they trained on. But what we want is we want models to generalize. So we want them to not just learn, but to also apply what they have learned to other kinds of data sets. Okay. So you can now see how easy it is. This is really the main thing, right? That's why I broke it down. So you do the test train, and you can check out how the test and train looks like, right? You can look at all of that. So we've split it, right? So the X train and X test. So when you are doing train test, you specify what percentage of the total data set, which is the X and Y, that you want to use for testing. So 0.2 means typically I want to use 20% of the sample for testing, and I want to use 80% for training. So typically that's what you do. You normally will use a small number. In fact, if the data set is really large, the number you use for testing should even be much smaller, right? If you have really large data set, you might even reduce it to 90-10 or even 95-5, right? But in most cases, 80-20 is a good split, or 90-10, or like 70-10-10. So it's always a good split. So that's the test size. So it's going to split based on that, and you will see it. And then that's just it, right? For you to train the model, this is just the code. All of that plenty thing that we wrote here, right? Which does exactly the same thing. All of this is hidden under the hood, but it's good to understand what these things are and how they do it. So all of that is hidden under the hood in this single random forest regressor, which is similar to what, random forest, train that we got here, right? So random forest regressor. So again, remember the parameters you pass in, the number of estimators, this is the number of trees that you want, number of decision trees. The more, the better, right? Then the max features, this is what you want to use to calculate, max features. Number of jobs, right? Well, this is where you want to do parallel processing. How many um, jobs, or how many what do you call it, threads of computation at the same time. Random state is just a kind of number to initialize your random number generators. So this number brings a bit of should I say, consistency, when you are using random numbers to randomize stuff. And then you run fits, and that's it. So this fit is going to run and train the model. And take note, you didn't need to specify any number of epochs, right? Because basically it's using, you've given it stopping conditions already. The stopping condition is to minimize the, what do you call it? The Gini impurity, measure, right? So of course, when you fit, this gives you a model. So we can do model equals, um, so after that, you can just predict. You can just predict. And you give it a test value and it will predict. You can give a single value and you can predict. And if you want to, you can also calculate mean square error, right? You can calculate mean square error by importing the mean square error function from the sklearn metrics. So remember what I said, sklearn actually gives you a lot. And we are going to kind of delve into sklearn a bit more. next week, right? And use it for a lot of things. We'll not break into a lot of all these other things anymore, right? We'll just start using sklearn and do a bunch of stuff. So this is how you can do um, you know, using sklearn, how you can basically do random forest. This is basically the same pattern for everything. Now, if you want to do, let's look at also doing um if you want to do use support vector machine, which is the other thing I mentioned, right? You can also do support vector machines. So this is an example. If you want to classify with support vector machines, we may not have time to um, we may not have time to go into this, but this is again sample code for it. It's again very simple, right? First of all, you just start off, you import sklearn, and then you load your data set. So this is a classification problem. So you support vector machines mainly for classification, right? Um, so this allows you to load the data set. So you can look at, this is a classification problem, and then you can look at the data set here. So you can see that the Y values are zeros and ones, basically labels of true and false. Okay. Then these are the X values, right? Which could be anything, you know, similar to what we did before. So with this now, you could even check, let me see, I could check out the size as well. So, um, so if we scroll to the top, we'll see the shapes. So 500, 500 data points. So with this, again, you do the test train split. This is basically the same thing. This is the same function, right, that we used before. So again, we split we can also check out how it looks like after you split. Okay. So again, we are using a 0.3%, that's 30%. So the test data is 30% of the total split. So remember, this one is 500 data points, right? 500 samples. So 30% is used for testing, while the remaining 70% will be used for training. So how do you train? Same thing, right? You create the SVM kernel. So you specify the kernel that you want to use, RBF, there are a bunch of other ones, right? And next week we'll look at it a bit more just to talk a little bit on the different kernels and what each of them mean. We won't go into all the maths for these ones, but it's kind of just having an understanding. So fit, when you run the fit, function, that's what trains the model. You give it the X data and the Y data, right? And it trains. And once it trains, then you can predict. And you can even look at the predictions. And then you can do an evaluation. So here we are using F-score, precision recall F-score, right? We'll talk about this next week when we're talking about how to evaluate performance of model. Okay. Um, so that is SVM, right? So truth of the matter is with sklearn, you can do anything. You can basically, somebody will tell you, oh, use SVM, and you just do it sklearn without even really knowing what SVM is, right? So this is a very powerful library. And what I would ask everyone to do is go check out their documentation, check out the docs, right? And go check out the documentation. There's a lot you can do with it, right? Um, I think they even have some neural network stuff, right? But the question is, you know, um, how good is their neural network implementation, right? So, but when it comes to neural networks, right, they really, they really best tools to use or frameworks. You will now talk about them, TensorFlow, PyTorch, and all of that when it comes to deep learning. So that's it. Um, I won't go further, but I would advise and recommend go check out Scikit-learn, right? You have a lot of stuff, classification. So the other things like gradient boosting, I didn't really talk about that in depth. I just went through it. But gradient boosting is a way of basically applying you know um, gradient descent for trees, right? So nearest neighbors, random forest. So well, next week we are going to just close the loop by talking a little bit about what all of those other things mean. The nearest neighbors, the TCA, the for you know the for unsupervised learning, then clustering. Then we'll also talk about um, dimensionality reduction, right? PCA and so on. So just there's a lot. So let's just see how much we can pick up. So I'll end it at this point and we'll look at the questions.